Hello, today we are going to learn about atomic emission spectroscopy. This is a method which is effectively used to identify and quantify elements like heavy metals. It is effectively used for this purpose. And in this video lesson, we are going to learn what it is about and how it is carried out. We are going to learn about the mechanism of this method as well. There we go. Okay, before entering into this topic, we are going to understand the differences between atomic absorption spectroscopy, atomic emission spectroscopy, and atomic fluorescence spectroscopy. Hopefully in the next lesson, we will learn about atomic fluorescence spectroscopy. And in our last lesson, we learned about UAV's atomic absorption spectroscopy. Those who didn't watch that video lesson, I strongly recommend to get acquainted with the contents of the previous lesson, UAV spectroscopy. So then it will be easier to understand the essence of these methods. Okay, atomic spectroscopy studies are about the interaction between electromagnetic radiation and atoms. There are three major techniques of atomic spectroscopy. As I mentioned, these are atomic absorption spectroscopy, atomic emission spectroscopy, and atomic fluorescence spectroscopy. In the atomic absorption spectroscopy, atoms absorb light and decrease in light intensity is observed. And atomic emission spectroscopy, atoms are excited. The electrons of atoms are excited and they cause the emission of light. So then the measurement is based on the emission of radiation. And in atomic fluorescence spectroscopy, the light is absorbed and re-emitted. Here there is a difference in atomic emission spectroscopy, flame or heat energy is given, and in atomic fluorescence spectroscopy, atomic electrons are excited with the light, and the emission is different from the absorbed light. Here is the same emission with the absorption spectrum. So the fluorescence intensity is measured in the atomic fluorescence spectroscopy. Atomic emission spectroscopy measures the light emitted again, which is excited, which results from the excited electrons of the atoms returning to their lower energy level. Yeah, I missed electrons here. Okay, next. This is about atomic absorption and matter. Electrons can only exist in discrete energy levels. This can also be called electron shells. They can't exist halfway between. Here we can see this is the ground state, and these are the stages where electrons can jump. And between these electron shells, there are no halfways as expressed here. The lowest energy level that an electron can be in is called the ground state. Yeah, this is the ground state. And in the ground state, electrons own the lowest energy. For an electron to move from a lower energy level to a higher energy level, it must absorb a set of amount, because a set amount of energy, because energy levels are quantized. As expressed here, as indicated here, when electrons move from the ground state to the excited status, to the excited shells, as indicated here, they absorb energy. Without some extra energy, we cannot expect their jump into the higher levels of electrons. This means that the energy absorbed by the electrons must be exactly the same as the energy difference between two levels. So that energy that's spent for the jump of electrons from the ground state to the excited states is always equal to those the energy that is absorbed by the atom for the jump of those electrons. When an electron absorbs energy, is it promoted to a higher energy level further away from the nucleus of the atom and is described as being excited. The term excited stands for the jump of electrons from the ground state in which the electrons own lowest energy to the levels where the electrons can be in a far distance from the nucleus. Okay, next. And this is about what happens after an electron becomes excited. Okay, electrons do not like being in excited state, which means as electrons are excited, they fall back to their ground state. This means that after becoming excited and moving to a higher energy level, they soon fall back to their original energy level. However, to do this, they have to release a packet of energy. This is called a photon. The size of the photon released is exactly equal to the size of the jump the electron had to make in the first place. This means here we can see the absorption and emission spectra of sodium, nitrogen, hydrogen, and oxygen. Every atom has their own light spectrum. Here we can see the absorption spectrum and emission spectrum of every single four atoms given here. The meaning is, okay, one electron, like sodium, has its own absorption spectrum, and these are the spectrum of the light that is absorbed by sodium atom to to have the electrons excited from the ground state to a higher energy state. And when those electrons are falling back to their ground state, they release the same spectrum of the light, the same emission that they absorb it while they are jumping from the ground state to the excited state. So the meaning of the text is that the size of the photon released is exactly equal to the size of the jump the electrons had to make in the first place. So what we need to understand is that every single atom has their own light spectrum, and in those light spectrum we expect the same absorption and emission spectra. The only difference that they are reversed. In the absorption spectrum, okay, the bands belong to the absorption. In the emission spectrum, the bands belongs to the emission of the light from those electrons resulting from their excited electrons releasing the energy while they are going back to their ground state. Okay, this is about absorption spectroscopy. Again, absorption spectroscopy is a technique used to measure the absorption of energy. Okay, the topic is about emission spectroscopy, but to differ and to deeply understand the differences and the mechanism of action of absorption spectroscopy and emission spectroscopy, we are going to repeat the absorption spectroscopy a bit. The absorption spectrum of a certain material is shown by a continuous band of color with black lines between them, as indicated here. The colored text parts represent the total light that is focused on the material. The black lines, as indicated here, show an absence of this light. These are the parts of the spectrum where the electrons have absorbed the light photons. As indicated here, for example, element A has this kind of absorption spectroscopy. Element B has this kind of absorption spectroscopy, and their mixture have this kind of absorption spectroscopy. By analyzing the absorption spectroscopy of many atoms, we can identify the presence of some atoms if the absorption spectroscopy of all atoms are gathered in one bank, let's say. It will be possible, it can be easily and automatically identified about the presence of some elements based on their absorption spectroscopy. Okay, there are two types of absorption spectroscopy, atomic and molecular. This means that both atoms and molecules have their absorption spectroscopy. And emission spectroscopy is mainly about the atoms, but in absorption spectroscopy, both atoms and molecules can be identified. I mean, the presence of atoms can be done by the absorption spectroscopy, and some functional groups of molecules can also be identified, suggested based on their absorption spectroscopy. In atomic absorption spectroscopy, the method is about producing a spectrum when three atoms absorb different wavelengths of light. This is usually used for gases. And in molecular absorption spectroscopy, this is the method of producing a spectrum when whole molecules absorb different wavelengths of light, usually ultraviolet and visible light. Again, let me recommend you to watch ultraviolet and visible spectroscopy given in the same playlist before this video lesson. Okay. And this is about atomic and molecular absorption spectroscopy. And next, now we are going to turn to emission spectroscopy. Emission spectroscopy is used to measure the photons released when an atom falls to a lower energy level after becoming excited. As indicated here, this is the emission spectrum of hydrogen. And the emission spectrum of a certain material is shown by a black band with separated colored lines. And these colors, the color lines are the parts of the spectrum where photons have been released from electrons when they fall to a lower energy level. Okay, differently, the spectrum can be shown here. I apologize for these discrepancies in the text and the figure. So this kind of differences in the intensities of the light spectrum belongs to the wavelength of the light where we can observe the emission of those atoms. Okay, there are two types of emission spectroscopy, line and continuous. When the spectrum is shown as lots of lines separated by black spaces, it's a line emission spectrum as indicated here. When the spectrum is shown as lots of colors in one particular wavelength, it's a continuous emission. Emission spectroscopy is used to identify a substance because of the energy released when the electrons fall back to their ground state is different for every substance. Again, for different substances, we can expect different bands, different emission spectrum. So based on the bands, we can identify the presence of atoms because every single element have their own unique emission spectrum. As indicated for hydrogen in this case, for example, hydrogen has four bands here, here, and one is here, which is not very visible. Okay, next. And this is about continuous spectrum, absorption spectrum, and emission spectrum. Again, this is the meaning of continuous spectrum. Continuous spectrum holds all wavelengths of light across a certain wavelength range. As its name implies, it is uninterrupted with no gaps, as we observe here. Here there is a gap. There are gaps, and the hot compact point of light emitted by stars is nearly a continuous spectrum, which means we can find out about, we can claim that the light is spectrum, an example to continuous spectrum. And how can we find out about the presence of hydrogen and helium in the sun? Is based on the emission spectrum of hydrogen and helium. When hydrogen and helium emission spectrum is studied, we can find out something, some bands like this. And if the continuous spectrum of the light is magnified and studied more deeply, we can see some differences. I mean, some not intense bands like this. So based on researching the continuous spectrum of the sunlight, we can find out about the presence of hydrogen and helium in the sun. And here we can see how the emission spectrum or the absorption spectrum can be identified, can be studied, and can be analyzed for quantification. So the bands are studied, and their peaks and intensities can be described like this. So by studying their bands, it will be possible to identify the presence of atoms based on their emission spectrum. Okay, next. And now we are going to turn to principles of atomic emission spectroscopy. Atoms in a sample are excited by thermal energy. That thermal energy can be given as flame, plasma, or arc. And electrons move to higher energy levels from their ground state. When electrons return to lower levels to their ground states, they emit photons, which are characteristic for some atoms based on their wavelength. And this emitted radiation is measured. The energy difference between levels determines the wavelength, and electronic transition is observed. When electrons drop from excited status to lower energy levels, photons are emitted according to the equation E, in which E equals hV, where A is the energy difference between the levels, ground level and an excited level of electrons. And H is Planck's constant, and V, this is not English V, this is Greekly, sorry for this discrepancy. The V stands for frequency of emitted radiation, and each element has unique emission lines. And here we can see the emission spectrum of unknown gas as shown here, based on the emission spectrum of different gases. We can find out about the presence of some atoms. For example, let's say we have the emission spectrum of unknown gas, and here we do not see any bands that belong to helium or argon. Yeah. So based on this kind of emission spectrum, we can exclude the presence of helium and argon, because here we do not see any kind of overlapping bands or corresponding bands. And oxygen can be categorized the same. Here we do not see something like that. And neon, here we can see neon have very close and very close bands like that. And here we can see xenon also show very close bands like this. So based on this kind of comparison, it will be possible to find out about the presence of neon and xenon. And today we have automatically identifying algorithm tools that enable us to automatically identify the presence of the atoms based on their emission spectrum. Okay, atomic emission spectroscopy is a method of chemical analysis that identifies elements within a sample by examining the intensity of light emitted from a flame at a specific wavelength. The wavelength found in the atomic emission spectra help determine the element's identity, as just I explained it. Notably, the intensity of the lines generated by the emitted light is proportional to the quantity of the element's atoms present in the sample. Emission spectra are typically produced when a low pressure gases atoms are heated or otherwise excited, such as by a strong electric field. So the emission spectrum results from the excitation of the electrons from their ground state to upper electron shells, which are far which are more far from the nucleus. So when they are coming closer and coming back to their ground state, they cause the emission. And then emission comes from the excitation, and excitation can be provided by providing some heat energy or some other factors like electric fields. So in order to obtain emission spectrum, the atoms have to be provided with the physical stimuli that cause the excitation of electrons from the ground state to a higher state. And here we can see how it happens. Atoms in the sample are excited by thermal energy. Again, it can be flame, it can be plasma, it can be arc, can be electric field. Electrons move to a higher energy levels. Here we can see this is the ground state. Yeah, from the ground state, electrons can jump to this state, the first excited state, the second excited state, the third excited state, etc. When electrons return to lower levels, they emit photons of characteristic wavelength. This emitted radiation is measured. Here we can see, okay, the electrons that jump to the farthest excited state uh, can release the energy, light energy with the highest photon energy. So let me remind you that the colors starting from violet and blue have more photon energy because they have smaller wavelengths. If you remember, we talked in our previous lessons, we said that the shorter wavelength, the higher photon energy. So here we can observe that the higher photon energy belongs to blue or violet colors, to violet and or blue colors, let's say. And so this comes uh, from the falling of electrons to a more far distance to the ground state. So the energy releasing from these atoms are expected to be more than other atoms. So the energy releasing from the green line or red line are expected to be less compared to violet or blue, because again, as I said, the wavelength of the red or yellow or orange or green colors is higher, and the higher wavelengths, the smaller photon energy. So this is about the differences. Okay, based on this spectrum, we can claim that argon might release blue colors, and these blue colors have, let's say, more photon energy compared to yellow and red. Okay, here we can see that hydrogen, the smallest, the simplest atom, has four this kind of bands, and neon and argon have more complex this kind of light emission spectrum because they have several times greater number of electrons. That's why their emission spectra are more, let's say, complex and diverse. Okay, this emitted radiation is measured again. When it is measured, so then the presence of atoms can be identified, can be claimed. The energy difference between levels determines the wavelength. Again, this wavelength belongs to atoms. This 400 from 400 to 750. Here we can see the visible light spectrum, actually from 380 to 740, 760. Yeah. And here we can see that the blue and violet colors belong to smaller, shorter wavelengths. That's why they have more energy, as indicated here. And here we can also find out that the shorter wavelength is linked with a greater number of frequency. For example, the violet color with the 400 nanometer wavelength have 750 terahertz frequency, and the frequency becomes smaller and smaller from the left to the right towards the red color, infrared color, and so on. Okay, next. And this is the continuation of that text. Each element possesses a unique set of possible energy transition. As a result, each element has a unique emission. And again, we do not see some kind of high similarities between the emission spectrum of atoms. For example, here we can see the helium and oxygen have highly differing spectrum. Even, for example, the atoms like neon and xenon do not have kind of highly similar emission spectrum. Here we can see some kind of close, let's say, spectrum, close bands to each other because they have similar, because they have the atoms in similar shells, but we also observe quite many differences. For example, here, here and here we can see, and in the red spectrum here, or yellow spectrum here, we can see quite many differences among them. So we claim that every single atom have their unique emission spectrum, which becomes visible when electrons release radiation in the visible light spectrum as they transition back to their ground state after excitation. The overall color is determined by the wavelength of the emitted photons, which correspond to their color. An emission spectrum is a pattern of colored lines superimposed on a dark background, with each line representing radiation released by an excited electron that has returned to lower energy level or its ground state. Again, the ground state is the state in which the electrons own lower energy, the lowest energy. So when they are given more energy, the electrons jump from that state in which lowest level of energy is owned to a higher energy level, which is far from the nucleus compared to the ground state. Okay, next. And here we can see the excited state of electrons, and the electrons uh, can go back to different electron shells, based on which we can see different bands as indicated here. This different bands comes from the uh, different number of electrons in those atoms, and in different shells, in the different shells of electrons in those atoms. So the reason why the hydrogen or helium have a smaller number of bands is linked with the small number of electrons and small number of electron shells. Each element has unique electronic energy levels. When electrons transition between these levels, they emit photons with a specific wavelength. Therefore, hydrogen have few lines, neon have many red, orange lines as indicated here, and argon have many blue and violet lines. These patterns act like atomic fingerprint. So every single atom have their atomic fingerprints. Importance of spectroscopy. Okay, this principle forms the basis of atomic emission spectroscopy. By measuring the wavelength of emitted light, scientists can identify the presence of different atoms in the given samples, and they can determine the elemental composition as well, and then detect the trace metals as well. So based on thorough analysis of the light spectrum, the presence of trace metals can also be identified. For compounds having a molecular weight higher than 3000 AMU, it is possible to identify them by using the mass spectrum, yeah? And the atoms cannot be identified by using mass spectrum based on those principles, and the presence of atoms in tiny amounts, like traceable amounts, can be identified by using atomic emission spectroscopy. This is about the detection of trace metals as well. Okay, electrons occupy quantized energy level. Light emission occurs during electronic transition. Each transition produces a characteristic wavelength. Here we can see, let's say this is the ground state of electrons. Okay, to this ground status, the electrons can come from the farthest electron shells, or close to electron shells. The ones that are coming from the closest electron shell causes the emission, holding the lower level of energy, which belongs photon energy, which belongs to red or orange colors. Yeah, and the ones having more energy releasing from the falling back of electrons that are coming from the long distance belongs to violet or blue colors, because they have smaller, shorter wavelengths, and the shorter wavelength, the higher photon energy level, as we talked a few times in our lectures. So here we can see this 656.3 nanometers belongs to red one, resulting from the falling back of the electrons located in the short distance. And the one, for example, having a violet color is coming from the long distance, and causing the 410.2 nanometer wavelength, which hold this high photon energy level. Okay. This principle forms the basis of atomic emission spectroscopy, where elemental composition is determined from the emitter's spectral lines. So based on this kind of lines, we are able to identify the presence of atoms. And in this figure, we can find out how the tool carries out the presence of different atoms. The figure was taken from the MDPI journal, MDPI article published in 2022, entitled "In situ detection of trace heavy metals, metal copper in water by atomic emission spectrometry of nebulized discharge plasma at atmospheric pressure." What we can understand from this figure that the liquid samples can be sent can be first nebulized and sent to the detecting place where the samples are turned into the plasma state, which is provided by argon atoms. So the emission of argon is excluded, and the presence of the copper atom can be identified. What I would like you to pay your attention to is the monochromator. Okay, monochromator stands for shorter wavelength of the light. I mean, it's not necessary in all cases to study the whole light spectrum. Based on this kind of short, let's say, range of the light, it can be possible to identify some metals. So it can simplify the analysis. So the light coming from the monochromator can also be effectively used to identify the presence of some metals, even if they are in trace amounts. So by using the plasma-like argon, the atoms are provided with the excitation stimuli. So then the light spectrum is determined and detected in the detector. So then automatically they can be identified. I mean, the presence of atoms can be identified by using some tools like this. Okay, next. And these are about the factors that might affect the emission spectrum. Here we can see the emission intensity of ethanol, methanol, and acetone. The red line belongs to acetone. So based on their differences in the emission intensity, some liquids should be selected in order to minimize the effects of different chemicals like the, oh, sorry. Okay, next. And here we can see the radar plot for each mean metal content. The figure was taken from another MDPI paper. And for sodium concentration, the unit is milligram per gram. Here we can see the sodium. And for other metals, the concentration unit is microgram per gram. By developing this kind of radar plots, it will be possible to see the concentration and compare the concentration of different metals in different samples as indicated here. And in this sample, okay, the microgram per gram concentration of copper, zinc, manganese, iron, magnesium, and calcium were studied together with sodium atoms. So, not only the presence of different atoms, but also the quantity of those atoms can be studied by using atomic emission spectroscopy. The point I'd like to highlight is that these atoms could be identified, could be analyzed, and for that the significance of inert gases are the significance of these gases deserve some attention. I mean, since they are inert, okay, they do not react with these atoms, so then it will be possible to see the emission spectrum of those atoms. If we use, for example, oxygen, okay, we cannot claim the unique spectrum of atoms as we have been talking in this lesson. So the atomic emission spectrum can be more complex, so it could be difficult to identify the presence of different atoms if we provide the plasma with oxygen or some other gaseous atoms that could react with these metals easily. Okay, next. Here we can see how the atoms are excited and studied. Here, for example, if we have metallic and salt solutions like, let's say, sodium chloride or magnesium chloride, calcium fluoride, the dense fog of atomized liquid particles are obtained. They are nebulized, vaporized, desolvated. By desolvating, we can obtain this kind of molecules in gaseous state. Those molecules in gaseous plasma state can be separated from each other, so the metals can be obtained, metal ions can be obtained. So the metal ions are excited. I mean, the electrons of those metal ions are excited, and while they are coming back to their ground state, they cause some emission. Based on those emission, by using CCD-like cameras, it will be possible to find out band passes, and by filtering those band passes, it will be possible to identify the presence of different atoms. And this is another example. The term is ICP-OES. The full name is inductively coupled plasma optical emission spectroscopy. This is a tool which is widely used in food analysis. And in food analysis, they can be effectively used, and they can identify the presence of atoms, not only the presence of different metal atoms, but also the quantity of those atoms, even if they are in trace amounts. So ICP-OES works by ionizing argon gas into plasma in a radio frequency inductive torch and introducing samples directly into the plasma. The high electron density of the plasma excites the sample again. Here we can see the excitation and promoting the electrons in it to higher energy levels. So they go to higher energy level. The photons are separated by wavelength, and the intensities of each specific wavelengths are determined by the photomultiplier tube or photodetector. In those tubes, photodetectors are provided, and so the elements can produce photons of several different wavelengths, yielding a specific emission spectrum with multiple characteristic peaks used to identify those elements in an unknown sample. So based on the identification of the bands, it will be possible to find out about the presence of different atoms as given in this example, like palladium, argentum, silver, gold, ruthenium, rhodium, osmium, iridium, rhenium, platinum, and indium. Okay, these are about studying the presence of different atoms, the quantity of different atoms by using inductively coupled plasma optical emission spectroscopy. Next. And now we are going to compare atomic emission spectroscopy with UV visible spectroscopy. Again, in our previous lesson, we talked about UV spectroscopy, and today we are learning atomic emission spectroscopy. I strongly recommend you to take a look at UV spectroscopy. Atomic emission spectroscopy uses the emission. So based on the emission of the light, we can find out about the presence of different atoms. And by using UV spectroscopy, we rely on the absorption of ultraviolet visible light. So based on the absorption, absorbed radiation, it will be possible to find out the presence of different atoms or functional groups. And atomic emission spectroscopy uses emission of light. UV spectroscopy uses absorption of light. In AES, we use the emission of photons. In UVV, so we use absorption of photons, okay, which is used for molecules. And atomic emission spectroscopy uses flame, arc, spark, plasma. Yeah, UVVs use just external light source like lamp. If you remember, we talked about the lamps in the topic of UV spectroscopy and colorimetry. Yeah, the lamps can be like deuterium lamp or tungsten lamp. Tungsten lamp develops visible light, which is from the ultraviolet. Which is from violet to red. Yeah, it's not wrong if we say from the some closer ranges of ultraviolet to infrared as well, based on the types of tungsten lamps. And the deuterium lamps develop the light like monochromatic. So in this case, the lamps, the light is filtered, and in this case, monochromatic light can be generated. Next. And AES tells us about the elemental composition. It does not tell about the molecules. And UVV spectroscopy can tell us about molecular structure and concentration. It will be possible to know about the presence of atoms in UVVs, but it is mainly used for molecular structure and the concentration of those molecular structures. Okay, and not to be more strict. Okay, we do not know exactly the same molecular structure, but we can find out about the functional groups, the presence of functional groups by using UV spectroscopy. AES tells which elements are present. UV gives information about electronic transition in molecules resulting from the presence of different functional groups. Okay, radiation source in atomic emission spectroscopy is excited atoms, and here UV or visible lamp. And sample state in atomic emission spectroscopy, atomized gas phase atoms. And in UV spectroscopy, it's a solution or a gas. Here, plasmas are used, and here solution or gas are used. And the detector in AES measures the emission, and UVVs measures the absorption. Again, atomic emission spectroscopy is in AES, atoms are excited and emit characteristic light, and in UV spectroscopy, molecules absorb light and electronic transition occurs. Next, in AES, trace metals can be identified. It is also used in environmental monitoring. It can be used in metallurgy, geological analysis, and UV is used for concentration determination, colorimetric analysis, in pharmaceutical analysis. It is widely used in biochemical analysis, in biomedical analysis, like proteins, DNA, glucose can be quantified by using UVs, as we taught in our previous lessons. Okay, these are all. I express my thanks to you, and I hope for your support with your likes. If you like the video lessons, so that the videos can reach a wider audience. Yeah, please support us with your likes. Thank you for your attention. Have a good day. Bye.